again, the next phase is going to be about structural modeling. So we will continue basics of structural modeling, the goals, and we will see many examples actually. We will talk a little bit about decomposition, and we will use also about graphs and how graphs can be used to describe structural properties. We will also talk a little bit about property modeling. So what we are going to learn now is the basics that you need if you want to use systems engineering tools. They mainly start with structural modeling. So you are just putting some boxes and so on. So we will cover now the underlying mathematical background to understand those tools, the behavior of those tools, and how you can interpret those kind of models. So let's go through static modeling. We will answer the question of how can complex systems be clearly modeled. So mainly this is really first steps of modeling. So this comes before thinking about the behavior and everything else. And actually, one more important thing is that there are many tools that support requirement modeling, and so this is also the basics of requirement modeling. So all these concepts are present in requirement modeling, and especially if you use SysML, the SysML language, that is the systems engineering language, you in the future you plan to use maybe the next version that is under development. There, the requirement engineering tools will use all the same concepts as here. So let's go on now. Let's start with an example from different domains. So I just bring the example from the architecture domain, where this building information model is quite often used now, and this is a new concept that you can use for modeling the whole building in a single model. And the most important thing is that if you construct such a model for the building, it is very good because you can have many different views of that building. And I will just show some of these views. So if you consider example of production office in a production hall, you can create a view of the gas pipe system. Actually, I don't understand this figure because I'm not an architecture engineer, but one can create a view of the gas pipe system. One can create a different view for the isolation or for the water and sewerage system. And they are all important views for different kinds of engineers from the same building. What also something that is more close to my domain is the electric installation plan. So today I was struggling to find plugs here in the office. So this kind of plan would be really helpful for me to start the first presentation in time. So anyway, they have different advantages, different kind of information. So you have the whole structural model of your system in the case of this office, and you can use it for different purposes. And whenever I engineer for example, I do computerized systems and software systems. I might also need all these different views for the different engineers. Let's consider, for example, if I'm a safety engineer, I need a different view from the system than, for example, a software engineer. And the different teams can collaborate only if they got those informations that they need, and they don't have to care about that information that is not relevant for them. So structural modeling is not just putting information into huge models, but it is also about organizing this information and providing for the different teams. So the goal of structural modeling is to divide the system in a way to make it simpler to design smaller units, and also very important to use already existing parts. So whenever you go to the industry and you are facing real systems, it is very, very rare that somebody starts a new project from scratch and nothing there is no existing parts. Especially because nowadays companies and okay, so we want to divide the system, use up already existing parts, use those things that were developed by other companies and so on, and put and build our system in this way to get some kind of high-level system overview. Also, very common use of structural models, and we are not only able to define structure of the system, so architecture, but to define data structures. So we can answer the question, what pieces of information should be there? And we can also use it to define the relationships between the pieces. So it's a very, structural modeling is a very, very powerful tool. Unfortunately, most people don't use for all these things, but I hope that you will do that. So let's do it a little bit more formal, because that's a university lecture and I have to be precise. So structural models are static and their bases are subsystems that are divided into their ingredients by the relation part of. So in structural models, we use this part of relationship. That's how subsystem and the system relates to each other. I will show many examples for that. So the ingredients for structural modeling can be the following. So we use the further divided subsystems, or we can use the elementary components that are those that are not divided further. The structural model represents structure of the system according to its ingredients, properties of the ingredients. We will talk about these properties later, and their relationships among each other. So how they relate to each other. So I just show an example robot vacuum cleaner because I have just had problems with my vacuum cleaners. So some parts had to be changed and repaired. So for example, robot cleaner has a control unit, has a roller gear, and it has a vacuum cleaner sub component too. So you can see that how we structurally divided this robot vacuum cleaner into parts. And what is an important thing is that so there is a difference between structural and behavioral modeling. So structural models are static. We have a wall and part and components and connections. For example, in the case, the main components of the robot vacuum cleaner actually are the control unit and the roller gear and the vacuum cleaner, as I mentioned before. And behavioral models. In behavioral models, for example, we use commands, and that will change some operation mode of vacuum cleaners. Behavioral models are dynamic. We have some kind of timeliness, states, processes, and behavioral models react somehow to the environment. So they define, for example, how roller gear should be controlled when some signals are received from the sensors. So, but this categorization is neither full or disjoint. So now we are in the structural part. So we have to capture the knowledge about the structure of the system. So what parts consist the system of? How are they connected? What kind of properties do the elements have? And let's take a closer look at the example of corporate network. So if I have, let's say, the structural, the architecture model of this corporate network, we can still answer interesting questions related to the structure of this example network that will definitely influence the behavior of this system. For example, we can ask the question of, is the internet reachable from that workstation? Or we can ask the question, if is the VLAN overloaded and how many computers are connected? And this question can be answered just by looking at the architecture, the structure. We can also answer, if is there a single point of failure in the system. So when you need some kind of fault tolerance, and that's many critical and mission critical applications need, then in many cases you can just even answer it by using the architecture models. And you can also ask such questions that what elements does the network consists of. So there are many interesting questions that can even answer at this level of abstraction just by constructing some architecture models. And another example, this is actually UML diagrams. So if you are familiar with UML, you might be familiar with this component diagram, and this is much closer to what we will use in the computer engineering domains. And when you are developing a satellite, you will definitely use this kind of representation, or if you are developing avionics control systems or automotive systems. So whenever actually we had this project together with Embraer many years ago, then we used these kind of models to answer all the analysis questions for the avionic industry. And they had very important questions related to fault tolerance and other stuff. So you can look at this diagram and use this diagram to answer, for example, the dependencies in the system, connections in the system, the possible connections in the system. You can answer questions related to what elements and connections exist. And you can go through the paths, and in many cases, these diagrams are used to check the paths that errors can spread on. So that's a very, very important question, because the errors are going through these connections and they might reach some that they okay, so I hope I could motivate to use all these models, because they give very, very valuable information when you are developing computer-based systems, either software or hardware or big complex systems of systems. We have to develop these models, and we have to use some kind of concepts to be able to develop these models. And one concept is the so-called structural decomposition. When we want to answer such questions, that what containedness relationships are there among subsystems, we use examples to show that. So, as I mentioned, structural models are static. Their bases are subsystems that are divided into their ingredients by the relation part of. So the definition of decomposition is the following. So decomposition, in other words factoring, is the division of a complex problem or system into smaller parts that are easier to conceive, understand, design, implement, program, and maintain. So we can use so-called hierarchical decomposition when we have multi-level whole part relationship. And when you develop a complex product, there will be some systems engineer that will develop the top level. And think about the system as a whole. And then they will divide, decompose the system into smaller parts, and they will give it to further decomposition and refinement to the other teams to develop some hardware functions, some software functions. They already find, for example, interfaces between the components. So they define how these small things can be put together. And it is very important to find the meaning of the part of relation, because you can think about it as a physical decomposition. So when you are developing hardware components together, that can be a physical decomposition. So in this case, part of is a kind of special division. But if you are thinking about the logical parts, the software, the functions, then the part of relations will define kind of functional division of the system, and especially the software functionalities and hardware functionalities. But it's very important to emphasize that you are using logical decomposition. At first, you are talking about functions. And when you went deeper in the development process, then you will find out if it should be a hardware or software. So in our experience was that in many cases in the industry, they at first they know what kind of functionalities they want to build, and they don't know if it should be a hardware or software. So it will be defined later, because in many cases, if you have a huge production, it's much cheaper to solve some problems in software and not in hardware. Because, well, software, you write it once. If you you develop some hardware, that you have to produce it many times, and it costs a lot. So they just try to put most things. They try to put as much things into software from hardware. They want to have these functionalities implemented in software. Actually, this is not true for all the industries, because if you don't produce so many things from a certain system, so then you definitely don't have to focus on this kind of optimization. So let's take a closer look at physical composition. So we define what pieces does it consist of. For example, in the case of robot vacuum cleaner, there is top cover, sensor module, and platform, corner brush, and many physical components. So if you have this vacuum cleaner, you can just put it together from all these physical components, and you can even disassemble it. So if you want to watch these components, then you are able. If you have functionalities, then you use logical decomposition, and then you want to answer question, what does it do? So it's around doing, it's around functionalities. So if I have a robot vacuum cleaner, then I can have the functionalities of discovery and navigation subsystem that consists of the moving subsystem, the sensor subsystem. It can have the cleaning subsystem, monitoring subsystem. All these are functionalities that you need provide the high level functionality of providing the services as a robot vacuum cleaner. And we can talk about correctness of decomposition. So the definition of correctness, the following: a decomposition is correct if each element of the system resulting from the decomposition corresponds to an element of the original system. So composed elements have to correspond to an element in a whole original system. Each element of the original system corresponds to some elements of the system resulting from the decomposition. So that's the opposite direction. So that actually means that we have the relations between the decomposed elements to the original elements. But I guess that's quite easy. So here is an example of correct decomposition where we want to get the whole system. We have further not detailed building blocks. Actually, in practice, in many cases, we don't know all of them. Because, for example, we don't know all of the Lego bricks, but I can just tell that, okay, we need these bricks to decompose the system and be able to build the system. And what is also very important in this Lego example is that we can have interfaces within a subsystem that will define how we can put the things together. And we can have also the interface to the outer world. So I mentioned in my previous presentation that you have the system and there is a context and you need this interface. So here in the Lego example, you definitely have this. And whenever you are putting together these parts, you need a service catalog. So you have the functions, the parts, and you use them. They are in the catalog, and you put your system together. And well, actually, you will get the system. So whenever you decompose it into smaller parts, uh, you can have such building blocks that you can produce. And then when you are producing these small systems, then you can put everything together like it is in the figure. So the Lego systems are very example
for composition and decomposition.
Top-down and bottom-up. This is how we develop our system mainly. So in the top-down development method, when we have the system divided to subsystems and subsystems of subsystems until I reach the building blocks, the bricks in the previous example. It's a very important advantage is that the roles of the subsystems are already known during the development. But the problem is that there are no functioning parts during development because we still have to refine, and decompose. So we go to the implementation quite late. And there is also drawback is that the problems and the problems regarding the subsystems are revealed late. On the other hand, we can use the bottom-up approach to build a system. And an advantage is that the subsystems can be tested step by step. And there are always some functioning parts during the development, but the exact roles of the subsystems are revealed late. And what is important in these development methods is that they are not only used in structural modeling. And another thing is that we used to combine them. So it's very rare that you just choose one of them. That's common that if you are developing cyber physical system, critical system, mission critical system, that you have to combine both approaches because you use the bottom-up development mainly during the hardware and platform development, in the sense that it's very rare that you develop everything from scratch in the hardware system. So you have some processors, you have some sensors, and you try to put together the system. And on the other hand, when you are developing the software functionalities, it's more often, we use more often the top-down approach because then we develop things this way. Another important thing is that nowadays, when we use more and more off-the-shelf software components, software libraries, then this bottom-up approach is appearing more and more in also in the software development. And also a very important thing is that we can also combine them in an iterative manner. And if we have time, tomorrow I will show, I guess, a nice approach that we developed and used with the industry. That combined iterative development with all these approaches, and we used various testing and verification methods during the development. Okay, so we also interested in how to represent these structural models. So we want to answer what kind of relationships are there among the subsystems. So we will use graphs, and I hope that most of you that have heard about or used graphs. So we will use these graphs. Actually, humans use these graphs because the human way of thinking is connecting things. So things can be anything in our minds: persons, airports, areas, anything, and we like to make connections between things. That can be dependency, or that can be the acquaintance connection between persons. It can be some kind of containment, but anything in our mind. And sorry, but my colleagues just come and need my key. So, but if we are not thinking, but we want to draw these things in our computer, then we need a mathematical formalism that our computer is able to handle, and it is formal enough. So they are called graphs, where we have nodes, edges, and properties. So when we are aiming graphs, graph can be so confused like this one, but our goal is to somehow, and this is actually, let's say, a graph that that was drawn in Xmind, that is a mind mapping tool. So this is when we want to express our thoughts in a computerized way, but that is not what we can really process during the systems engineering process. So in the computer engineering, everything has several often contradiction definitions, and when we are developing graphs and structural models, that is the situation is the same. So we have to think about what we consider a system and what we consider a model. And whenever you use systems engineering language, that will help you to precisely define these things. And in computer engineering, the same term is often named with different names. So for example, if I'm talking about graphs, I can say that I have nodes, vertices, objects, or concepts, and the connections can be called in other ways, such as edge, links, arcs, relationships. And the important thing that you should always pick one, that's how you call them, and that makes talking with other engineers much easier. And actually, this is still a problem if you use engineering tools and engineering languages, because there you can also combine these different names for the object. So basic stems, if there is a graph, this is called G equals as the set of nodes with the set of nodes V, and we also have a set of edges that is called big E, that can be directed or undirected. And well, we will also talk about that the nodes and edges may have labels and colors. So that is the basic term. We have a graph with nodes and edges. And what we are going to use, and it's a very important concept in graphs, and also whenever you use systems engineering model, is the transitive closure. The transitive closure of a graph G is another graph that is called, let's say, G star, that contains the nodes and different set of edges, E star, where we say that an edge is between two nodes if there is a path from between the two nodes. So we need this transitive closure to answer many questions related to our structural models and graphs. And now I will just show some examples from different domains. So I will just, so you know, I mentioned that I'm from Budapest, I'm from Hungary, and we have a public transport network there with different metro lines, underground lines, and tram lines. So here you can see the map of Budapest and with the many lines. But now we will focus on only some lines that are depicted. They are called M2, M3, M4, and 4-6. They are lines in Budapest. So whenever you go to Budapest, you will use these lines. And we can just filter the view and show the stations and the lines, the connections between them. And you could see that we depicted with colors the different types of line. So whenever you see different colors, then in coming to the station, then you have to change from one line to other. And for example, this representation can be used to answer shortest path questions between them. So if I also put some additional information into the structural model, that is namely the length of the route, the travel from one station to another, then by using the transitive closure, the definition of transitive closure, and summarizing also the time needed to go through all the parts of a path, then we can answer such questions: is that which is the shortest path to go somewhere. And we also have very powerful tool called filtering. For example, in this case, by edge labels. And we will get some subgraphs of the original graph. So we can, for example, remove the line, the tram line that was 4-6, that is the yellow. And we can just focus, for example, on the underground network only. And we can answer the question that what is reachable by the underground only. And we can use it to answer reachability and other questions. So we had the structural model, and we can develop different views of this model. And now the example is the public transportation system. But whenever I'm developing a system model, for example, a critical system, then I can use similar questions to answer. For example, if there is a single point of view, single point of failure, in our system, I can find the weaknesses in my system and so on. And also another important thing is that these stations are in some areas in the system. So we can have some kind of allocation, some kind of containment. And that is quite similar what you are using in for example, in satellite developments, because you will have different hardware components that we contain other hardware components that might contain different functions. But that's also the same in the automotive domain, when I have many computing units. They are connected to each other, and I want to put functions to that computing units. And that's the same also in the avionic industry. So whenever we worked for Embraer, we had the same problems, but it was not Rákóczi Square and other squares and underground stations and underground connections, but it was about communication networks, computing units, and functional. So let's see an example. We have districts in Budapest. I do not know if you have districts in San Jose dos Campos, but I'm sure that there are parts of the city. For example, I stay in Jardim Aquarius. I hope I pronounce it well. So there are some parts. Here in Budapest, we have Leopold Town, downtown. Actually, if you go to Budapest, you will definitely go to the downtown because there are always parties there. And these stations are mainly in these different parts of the city, and especially now in the 5th district. And we can create a hierarchical model for the parts of these 5th district. So, for example, we have Leopold Town in the 5th district. and the downtown. And in Leopold Town, I have Deák Ferenc Square, Kossuth Lajos Square. Actually, they are famous. They are named after famous historical people from Hungary. And the Square of the Francians, that is in the downtown. So you have this hierarchical model of that graphical representation. And whenever you are developing these systems engineering models, you will have quite similar representation that what you have in the right side. So this kind of graph-based representation will be in your computer, and that is what you have to process. And whenever you are developing tools, then you are doing and you will dealing with this kind of representation. And the left side is some kind of very nice graphical representation that helps the understanding. So what can I do? So far I had simple graphs. I had the transport network that was an undirected graphs with the lines and the stations. And in computer engineering, I mainly want to use directed graphs. So I might be interested in how can it be made directed. Actually, it's not so difficult because I just substitute each undirected edge, which the edges to both directions, and this can add more information to my model, and that's an important trick when I'm developing structural models. You don't necessarily have to use it, but in many tools you must have directions. So from the simple graph, I want to go to the typed graph. So I want to give some type information for the different parts of my simple graph. And I can do it in a way that I assign the different districts of Budapest to the different stations in our transportation graph. And I can assign this way types to the elements of the graph. So this way I will have even more information of my stations because they will have this kind of type information. So for example, I have these 5th district stations, or 8th district stations, or 9th district stations in my graph. So that is an added type information. And let's take a look at on a software engineering example. So we have this calculator, and this is on all Windows machines. I'm sure that you are all familiar with it. And what is important is that I can also represent it in a tree structure, so as a graph with all the containment relations. So what can be the containment relations here? What are the parts and the sub-functions, sub-parts in this calculator function? So at first I have the window. That's the main thing here. That's the root of my system representation. And in the window, I have the menu on the top, and I have the main window, you can see. And inside the menu, I have this view, edit, and help parts. And in the main, I have the display. There is this degrad part that will contain these degrees, radians, gradients. There is the MC part. And actually, okay, and there are many other buttons, but for the sake of simplicity, I didn't put here. And in the degrad part, I have the degrees, radians, and grads. So whenever I want to push a button, like the radians here. So I want to switch from degrees to radians. Then I can start finding that part by going from window to the main part, to the degree part, to the radians part. It's very important that in this functionality, when you are doing this, at the degree part, you will also know that, okay, when I switch to radians from degrees, then I have to deactivate, uncheck the degrees part. So that will be also contained in this chain of events, actually. But you can see that to provide my functionalities, I had to traverse this structural model of my software and go and find those parts where I will work. And I want to emphasize that, okay, this kind of tree structure, it's quite common in computer engineering. So whenever you are just browsing your file system, then you will also browse this this kind of representation. And so here you can see that I have the root directory, I will have documents, pictures, and I will have files in the pictures directory, and so on. And this way you can answer, for example, such questions that how much storage capacity can be gained by deleting the directory document. So I can check it because I can just go there through this tree structure. And let's go further. Such file system has some characteristics. So if I want to answer the question that how much storage capacity can be gained by deleting the directory documents, then we need some further parameters. So in this table, you can see that we provided the size parameter. And knowing these pieces of information and the file hierarchy, this question can be answered. And you see this file system example, but this is not just about file system. So whenever you are developing systems engineering model, you will always use this kind of properties of your models. So we have to talk about how to model the properties in structural models, and what properties do have the individual components. So definition of property. So we can model properties and describe properties. So the property is a quite general thing. So the property is a function that is defined over the elements of a model, and it is partial. So it can happen that values may be undefined, and they have a value set of which is the set of the possible values of the given property. So the given property has a possible value set. Let's see it in our example. So if we consider the structural models in a tabular representation, and I bring this tabular representation because in many cases people just think about the structural models as graphs, but actually they can be represented in a tabular form, and it's very important to know and use. So the rows of the table are the model elements, and I can use this. So the rows are the elements of my model, and the properties are the columns of my model. And I can see that I can have these empty cells. That is when we don't have attributes. We don't defined. So that's why it's called partial. And in this tabular representation, it is very easy to use operations. And what kind of operations can I think of? And one is filtering. And during filtering, a filtering condition is evaluated over the elements of the model, and the submodel is kept that consists exactly of the elements satisfying the condition. So, for example, if you want to filter only those elements in the previous example where the type is file, I will just get these results. And if I further filter to those elements where the size is bigger than 1000 kilobytes, then I will just get one element. So that is how filtering works. And we also use projection, and we will also define projection on this tabular form because it's easier to understand. So during projection, some parameters of the model are chosen to be kept and others are omitted. So we have the example here, and we want to project this example to name and size. Then we will get another table or another graph with only the names and the size. And actually, I'm sure many of you have already used SQL. So if I write that select name and size from data set where type equals file and size is bigger than 1000 kilobytes, you will understand it. And the first step, when I select the name and size, it's a kind of projection. And I define the data set, data source by this from keyword. And then I filter with the keyword where. So I filter to the file type and also for the elements that has size bigger than 1000 kilobytes. So SQL, that is called structured query language. That is a data query language, data query and manipulation language, and that is the basics of relational databases. And we can use it as a description language to define filtering, project, and derivation. And if you learn about databases, you learn much more about these query languages. But what I want to tell you is that if you use modeling tools and you define structural models, you will use for creating different views and different other models. You will use SQL-like languages for that. So it's very, very important to learn SQL even if you become a systems engineer. So let's go and let's go to see how we are modeling times. And actually, I just put this example because I really like it, but I will also use another example that is much more simpler, where I think it's quite relevant in MP. So the galaxy has some areas, there are some containment relations. So we can describe this kind of knowledge with graphs. So for example, we have the galaxy, forwards, outer rims, and we have elements inside these galaxies. I just bought the example from the Star Wars. And we can use it to answer questions. And what I want to show is types and attributes. So whenever, for example, I have these galaxies and planets, what happens if I want to say that okay, planet has a color, and in Star Wars, if I define the color of the planets, I can have colors of many other things. So if I can just consider Star Wars, there were there was also color for the lightsabers. And should we put them together, or should we put them to different parts of the model? And it turns out actually that these properties will belong to elements of my models, and different elements can have similar properties. So let's define types and attributes. So type is a part of the knowledge that is implicitly expressed in the label. And type is a special property, and other properties are attributes of the system. We will see some examples of it. And a widely used convention that is you have to remember whenever you are developing models and so on, that attributes may sometimes change. They don't have to, but they can change. So for example, if I want to talk about the color of a lightsaber, okay, that wasn't change in Star Wars, but let's say that the color of a planet can change regarding or depending on the sunshine, for example. So the color can change, for example, but the type is permanent. It will never change. So if I have a special type of planet, that planet will have that type, even though its color can change. So we can have type graphs. So we will have type node for each node type, and the type edge for each edge type. So this is actually the meta model in our system. So in this example, a line can be an underground line or a bus line. So a line, an underground line is a line, and the bus line is also a line. So we can just tell the types of the nodes, and there is this special relationship that is a that refers to subtyping. And what we can express this way is that if they have something in common, and in this case, the bus line and the underground line, they have many things in common, and we put this common information into the line type on the top. So in the left side, you can see that the set of lines can have, there are in the set of lines a subset of underground lines and bus lines. And we will use this kind of information. So we defined sets and subsets in the Word. And we will use these sets to give type information for the elements of my model. And how can I do that? We will have labeled type relations among type nodes. So for example, if we go back to this example here, we define the lines and the depots. And we can also new information between them. So for example, lines connects to other lines. And the lines are served by depots. And here in the meta model, in the type graph, loops are possible. So here we want to define the building elements of my model, and I can attach with this connects to relation different lines. And we can have also this kind of directed connections. And that can be sometimes difficult because different parts of my model can be in different models or store different storages, so that can be sometimes. And if you are thinking about this meta model, it's not complete in the sense that something is missing. For example, a bus line can only be served by, so bus lines can only be served by bus garage because the bus can't go down to the underground. So this served by relation from line to depot, it will not capture all the necessary information. You will learn later how I can add more information because the bus line can only be served by the bus garage. And I can put this type information to the instance graph, because here we have the instance of relation. So in the instance part, and that is actually the lines in Budapest and the different depots in Budapest. And the lines have the type. So for example, it can be an underground line. M3 is also an underground line. But number 7 and 8E, they are bus lines. They are connected. So those are connected that are connected in the city. Not everything with everything else, just we design the routes in the city. And you can also have this served by relationships here that you can see. And also the garage and the underground train remise is here. So here, the type of this Mexico route is that it is an underground train remise. That is also an underground train remise. But here, that's a bus garage. That's actually a huge bus garage. And that is also a bus garage. So we provided type information into our instance model. And that way we provided more information. And so we wanted to answer the questions if the instances correspond to types. And an interesting question is that, okay, I defined the type graph. So what are the possible types? Can there be any further types? And whenever we are thinking in the closed word modeling, actually, I use this kind of models to define all possible parts. So as you could see on the top level was the type graph, actually the meta model, and then comes the instance graphs. And as I mentioned you, this information can be put either into graph, or they can be they are also present in programs. So if you consider programming, then they are present in programming paradigms that are actually the theoretical model of a programming language. So you can use structured programming, And for example, you can organize variables into structures. And that's kind of type information. And then you can use the structures during the runtime of the program. Or you can use object-oriented programming, where the type is a class and the instance will be the object, and the attribute will be an attribute field, and the operation actually will be a method. So you can also set visibility of attributes, methods, so you can further refine those kind of type information that we have seen before. And you can have pointer fields, nesting, and many other things that are for designing references, composition, aggregation. So in object-oriented programming, you have the same concepts like in this structural modeling. And you can have the inheritance. And if you remember, we used the is-a relationship between elements, and this is quite similar to inheritance. And actually, there is a widely used modeling tool to define metamodels and models, and especially structural models. It is the Eclipse modeling framework. I mention it because it is used in the industry quite widely. So if you go to the avionics industry or to the automotive industry, most of the tools are using this Eclipse modeling framework where you can just develop your metamodels and models. And it supports it. It's very good because it has many advanced features such as automatic saving, loading, and you can check actually the instance models. And it's a very powerful tool. It's not so easy to use it, but it is widely used. And there are many other representations for models, for example, textual representation, XML, JSON, and graphical representation such as UML, EDL, or the SysML that I mentioned in many cases. And when I guess soon the next version of the systems engineering language will came out, and it will be much better than before. And you can also use XML, JSON, as I mentioned, that are standardized universal technique for the definition of description languages. They are human readable, and yeah, and as I mentioned, UML is the unified modeling language, that is universal modeling language for software development, and as I mentioned, SysML is a UML-based general modeling language for system engineering. Actually, the next version will not be built on top of UML anymore. And in Eclipse, you can use this Eclipse modeling framework. And there are some examples that you can use. But anyway, I won't into these examples because I guess I run out of time. So I think we can stop the recording and we can go to the questions. So if you have any questions, please let me know. I got the question how to model aerospace systems using non-object oriented languages like C. Well, I mentioned that C is, it's a modeling language, but whenever you really develop complex systems, you will definitely use some kind of high-level language. And high-level languages are mainly using the concept of object orientation. So this composition, instance of relation. Okay, so whenever you are developing complex system, you don't have to use all the concepts. So you can keep it simple, but you have to use some kind of notation from these concepts. So, but what I showed you here, I think it's easy. It's easy to learn, and it's not so. It's also not too difficult to apply it in systems engineering tools. So for complex modeling aerospace systems, you will definitely have to use some kind of object-oriented thinking. But it's, believe me, it's not so difficult. So maybe tomorrow I will show. I will discuss it with Fatima and Professor Fatima and Professor Antonio, that tomorrow maybe I can have a last additional lecture where I just show some examples how you can imagine these systems in real life. So what we do. I don't have examples for satellite manufacturing. I can have models from the automotive industry. So, but if you talk with Professor Fatima and Antonio, we can work on developing such models together, and it would be great. But the project leader is Professor Fatima, so you have to reach her. So anyway, just ask her and we can find out some nice collaboration, because we can, I think we have a lot of experience actually in this domain by now. So we have developed a very, very complex system for the automotive industry, and I think that was at least as complex as what you have in a satellite. Okay, thank you very much for your attention. I'm really happy that not so much people left the presentation. Next, we will continue with state chart and state-based modeling. It will be presented by my colleague, Bence Grudge, and he's really an international expert in this kind of modeling. He also the developer of a very advanced tool that is used even by the industry. So it was used by in a project together with NASA. I'm sure that you have heard about NASA, and I'm sure that you have many collaboration with NASA. So we used his tool, project together with NASA, and he will tell you many interesting things about behavioral modeling, especially state-based modeling. He will start at the beginning. So if you haven't learned about that, you will be able to follow it. And if you want, we can still have tomorrow some advanced slides about how it's really used in the industry. So it's on you. If you are interested in it, please indicate somehow that you would be interested in, and then we can organize a 1 hour additional, half or 1 hour additional session around these topics. So you can just indicate it. So the next presentation will start at around 1:15. So I hope you will join. And if you have questions for the morning session, you can still ask it in the afternoon session. So thank you very much. Obrigado. And well, we will give you all the materials. Actually, I have already the PDF, but I do not know where I can put it. So I will just ask the organizers whether I can put it maybe in Moodle or somewhere I can put it. don't have access to the Moodle, but I will ask them to put into the Moodle. So you will be able to read them, and maybe I will ask my colleague to put the presentation slides before the presentation, so you can also use it during the presentation. Because for us, the most important thing is that you understand most of it, and maybe you can apply it here, because what we saw is that it is not only needed in IMPI, but in the industry here. Okay, so obrigado, and see you later at 1:15. Goodbye.
Thanks a lot.
Thank you, Andres. Obrigado. Bye-bye.
Thank you, Andres.
Thank you. Bye.
Okay, thank you. Very good. Thank you. See you later.